Today's topic will be about thermal conductivity, how to use transient and steady state methods to measure the thermal conductivity. So, first of all, I would like to introduce myself briefly. So, my name is Erika Hahn. Here you can also see a picture of me. I studied physics in Germany and I'm working for Linzai since 2020. Here I'm responsible for the application laboratory in regard of thermal conductivity and thermoelectric topics. My languages are German and English, so you can contact me via the email address shown here. For those who do not know Linzai, here's a short introduction. The company was founded in 1956 by Dr. Maximilian Linzai in Selb, which is in northern Bavaria. Here you can see a picture of him. Now the company is led by his son, as Klaus Linzai, and his two sons, so the third generation, Florian Linzai and Dr. Vincent Linzai, are currently the owner and leader of the company. Selb in Germany is here the headquarters of the company. Nevertheless, we also have own sales and also lab locations over the world. So we have a company also in the US, India, and China. And for the rest of the world, we have more than 65 dealers worldwide, which help us to promote and sell our instruments. The business field is mainly the construction, development of measuring instruments for thermal analysis, thermal conductivity, and thermoelectric materials. But we also offer service measurements in our service labs worldwide. On the next slide, you now see the product range of our instruments. So starting from classical thermal analysis with DSCs, TGAs, and SDAs, going further to dilatometers, TMAs, and a further broad field is the thermal conductivity, thermal diffusivity range with various instruments, as well as thermoelectric materials characterization. And then we have some further products helping in understanding thin films in respect of thermal conductivity and thermoelectric properties. Then we also have an instrument being able to measure the Hall effect, so also for semiconductor industry. What is unique about Linzai is that we don't have this standard product, so we offer a high level of customization. So, for example, high pressure instruments, high temperature instruments, nuclear applications, and so on. So, as mentioned, we offer a high level of customization, and more or less, not every instrument is the same, so every instrument is more or less unique here, what we build here. Today's webinar will be structured as following. So first of all, there will be an introduction into the topic. Then we will have a look onto each of the methods we offer a little bit more in detail. So the laser flash, the THB, the TIM tester, the heat flow meter. In the end, I will summarize that and give a guide on how to decide which method is the best one for the material. And in the end, I will show the outlook for the thin films and for the next webinar. So first of all, heat transfer, what is it and how can it happen? So the heat transfer in materials can be grouped into three groups. So radiation, conduction, and convection. Radiation is the emission of electromagnetic waves. All materials radiate thermal energy, and there's also the convection happening mostly in gases or liquids. So convection is the particle stream in heated liquids which carry the thermal energy. So a good example here is a heater with the water inside, or the Gulf Stream using convection for being able to carry thermal energy. And the big group in the middle is the conduction. So within conduction, there is no transport of material. The conduction can either be done via phonons, so by lattice vibrations, or via electrons, so freely moving charge carriers. In metals, the thermal conduction is dominated by the electrons. Here, there's this very helpful law called Wiedemann-Franz law, where the electrical and the thermal conductivity are set into relation using the so-called Lorentz factor and the temperature. So measuring one of the properties helps to find out the other one. In insulators, the thermal conduction is dominated by the phonon contribution, so the lattice vibrations, and in semimetals and semiconductors, both parts contribute. So one can recognize there are strong temperature dependencies, so that in one temperature range, maybe the electrons dominate. In another temperature range, then the phonon contribution is more prominent there. A very helpful picture to group or to understand the three mechanisms of heat transfer a little bit better is this one here. So here you can see the mechanisms of heat transfer shown in this picture, where we have this fire pit with using the radiation being able to heat up the pot with some water in there. Within the water, the heat is transferred via convection mainly, and after a longer time, also the handle here of the pot will get warm. That it gets warm is happening due to conduction, so that the thermal conduction of the pot transports the heat also towards the handle. So we will focus mainly today on thermal conductivity as well as thermal diffusivity. Here you can see in this table some examples for thermal conductivity, where you can see that the range is very huge. So, for example, insulation materials have a thermal conductivity even below 0.1 watt per meter Kelvin, whereas metals have a quite high thermal conductivity, and diamond is one of the highest material, or is one of the materials with the highest thermal conductivity of about 2,300 watt per meter Kelvin. So that it is a challenging task to cover all of these thermal conductivities being able to measure. So, as already mentioned, we will focus today on thermal conductivity and thermal diffusivity. This slide and next one should help to understand what is the difference of both. So, the thermal conductivity of a material is a measure of its ability to conduct heat, so a portion of thermal energy, and the equation can be seen here, so that you need the heat flow through the sample and the size of the sample, as well as the temperature gradient established by the heat transport. The thermal diffusivity, in contrast, is the measure of the ability of the material to conduct thermal energy relative to its ability to store thermal energy. So here we already see that the thermal diffusivity is linked to the thermal conductivity, and more or less you observe how fast a temperature difference is propagating within a material. So this is summarized here as well. So that the thermal diffusivity with the unit meter squared per second is the propagation of a temperature difference in the material, and the thermal conductivity with the unit watt per meter Kelvin is the propagation of a heat difference in a material. So both of these properties are directly linked to each other by this equation. This is often used in practical measurements, where we measure maybe a part of the properties and then calculate the other one using this relation, so that the thermal conductivity is the product of thermal diffusivity, specific heat capacity, and density. The key point here is that all of these properties are temperature dependent, so that one needs to perform temperature dependent analysis of each individual property to have the most precise result in thermal conductivity. But why is it so important to know the thermal conductivity? The thermal conductivity is a very crucial parameter for the design of a device. So especially if you're planning some heat management, it is needed to do some simulations to find out which materials are in contact to each other, how is the heat propagated. So for that, mostly simulations are done in the end, where one needs the material parameters to be able to do the simulation. Also, a simulation of casting, solidification, and sintering processes need a thermal conductivity. So here is an example where you can see a material where the thermal conductivity is depending on the thermal pretreatment. So you see different classes of material and different pretreatments, where you see thermal conductivities ranging from 20 to about 45 watt per meter Kelvin, just due to different processes. Additionally, the thermal conductivity is also an indicator of quality. So if you want to build in a material with a certain thermal conductivity, being able to have the good heat management, then you of course need to guarantee that this material has really this estimated thermal conductivity. So this helps also, or this is also useful for quality control. So here, for example, you can see what can happen if the heat management is not designed very well, where you just get a crack in the material as a consequence of thermal stress, where maybe the heat is not brought away from the parts. Also, for example, in electronics, you need to make sure that the electronical parts do not get too warm. So that you need to use a heat sink to bring away the heat from the electronics. Basically, the measurement methods for thermal conductivity or thermal diffusivity measurements can be grouped into two classes. On the one hand, we have the transient methods, where the sample is subjected by a thermal disturbance, and this disturbance is observed as a function of time. On the other hand, we have the stationary methods, where also a a thermal disturbance is brought into the material, but we wait until a stable temperature gradient is established through the sample. So this is also seen here. The transient state is directly looking at when bringing in the thermal disturbance into the material. The steady state methods just take a bit longer, and we wait until there is a constant flow, heat flow through the sample. This having a look directly as bringing in the thermal disturbance gives also the advantage of the transient measurement methods, where we have a short measurement time. Additionally, an advantage of this transient methods is typically that a very broad thermal conductivity range can be covered within one method. Also, a broad temperature range can be established. Disadvantages in case of the laser flash, for example, is that only thermal diffusivity is measured and not directly the thermal conductivity. Furthermore, mostly these transient methods have a complicated theory behind that, because you need to model the heat transport within a broad range of materials within a very short time. And this is typically quite complex. To the transient methods, the most important techniques are the laser flash technique and the hot wire or hot strip hot plane method, which we will have a look on in a minute. The most well-known stationary methods are the so-called plate methods, to which the guarded hot plate technique belongs to, the TIM tester as well as the heat flow meter. The latter two we will have a more closer look than later on as well. The benefit of the steady-state methods are that the data evaluation is very simple compared to the transient methods. You directly get the thermal conductivity based on the relation I showed before with the heat flow and the temperature gradient and the size of the sample. You can easily calculate that. Disadvantages is that the measurement time is quite long. Additionally, the thermal conductivity range is also limited, so mostly or maximum moderate thermoconductive materials can be measured, and the temperature range is also more limited compared to the transient methods. Here you see the thermoconductivity instruments lint size offers. We have the most universal tool, the laser flash analyzer, then also the transient method called transient hot bridge based on the hot wire technique. And on the right side, you see our steady state methods, which are the TIM tester, the thermal interface materials tester, as well as the heat flow meter for insulation materials. This slide should give a short overview of the thermal conductivity and application range of the different instruments. There you can see that the laser flash and the transient hot bridge method cover almost the complete thermal conductivity range. Also, they offer a very broad temperature range, up to 700 or even up to 2800 degrees Celsius. The TIM test and heat flow meter are a little bit limited regarding the thermal conductivity range as well as the temperature range. But depending on the application, one of those tools might be the ideal one, the best fitting one. So now we start with having a look onto the instruments a little bit more closely, onto the measurement methods, and we start here with the laser flash analyzer. The laser flash measurement is the standardized measurement principle according to the ASTM E1461, and it is described where a small, thin disk specimen is subjected to a high-intensity, short-duration radiant energy pulse, and the energy of the pulse is then absorbed on the front surface of the specimen, and the resulting temperature rise at the rare phase is recorded. This is illustrated here. So we have the power source, the sample, and the infrared detector as the main parts. The power source shoots a short, high-intensity pulse towards one side of the sample, and we have a look onto the rare surface with an infrared detector and collect a signal, which looks like that, where we see the temperature rise with time and then the decay of the temperature just due to heat losses. Out of that curve, the thermal diffusivity, is calculated using also the specimen thickness and the time required for the rare phase temperature rise to reach half of its maximum value. So this you can see here, graphically illustrated, where we find out half of the maximum and then use here the time of that to be able to determine the thermal diffusivity according to this formula, where we have a constant here, the sample thickness, and this half-time rise. This basic setup is realized in the instrument a little bit differently, so it's not horizontally aligned but vertically, where we have on the bottom the power source. We offer here two series, the LFA 500 series and the LFA 1000 series, where the main difference is the power source. On the one hand, we have a xenon lamp, and on the other side, we have a laser source. The xenon lamp has a lower pulse energy compared to the laser source, so it depends on the kind of materials which we want to investigate, which type of model fits the best. But basically, both setups are similar. So we have on the bottom each the power source, then we have the furnace, where the sample robot is located. So we have here different sample robots, up to 3 or 6 samples. Also the furnace types, there are a lot of different types, going from minus 125 degrees Celsius up to 2800 degrees Celsius, depending on the furnace type. On the top, we have then the detector. There we also have different options. So either Peltier cooled, so thermoelectrically cooled, or liquid nitrogen cooled. So you already recognize here probably that there are a lot of different options on how to customize, build up a laser flash according to the needs of the application. So on this slide, you see here the sample robot as well as the different sample holders. The laser flash analyzer generally is designed for solid samples, for bulk materials, more precisely, but you can use it also for liquids or pastes, fiber materials, and so on. So more or less all kind of materials, but you might need a special sample holder for that. So typical sample size is about a 1-inch diameter or a half-inch diameter. Basically, also slightly smaller samples are possible, or one can use also square samples. To the sample preparation, you need to coat the sample on both sides with some graphite spray to ensure or to maximize the absorption of the thermal energy shot out by the laser or the xenon lamp. Then we have here the specially designed sample holders, where you just place the sample on top, and we make sure that the sample is in as less as possible in contact with the sample holder. We have here a lid closing just the side so that no excess light hits the infrared detector. So for the sample robot, we have either a carousel for 3 positions or for 6 positions. These are the standard ones. We also have one up to 18 samples to maximize also the sample throughput. The sample robot is then located here. You see it here a little bit more in detail. In the middle there is the sample thermocouple measuring the sample temperature. So as mentioned before, the laser flash is also able to measure powders, liquids, or pastes. For that, we have the special sample crucible where you fill in your amount of liquid, for example, and then you just have a closed sample crucible. But also for the higher temperature range, we have here some excess volume on the sides so that the sample can expand during the measurement without spilling out of the crucible. And in the middle here, the sample thickness is well defined by the bottom and the lid of the sample crucible. So I mentioned before that we use this, let's say quite simple formula of thermal diffusivity calculation with a constant sample thickness and half-time rise. It's not as simple as shown on the first line of the laser flash, so we do not evaluate the curves graphically, but there are some mathematical and physical models behind that, being able to fit the evaluation model to the data, because basically the laser flash setup assumes an adiabatic state, so the ideal state. But in reality, there are some non-ideal conditions like heat losses from the sample to the surrounding, to the sample holder, and so on. And the so-called finite pulse length effects. This happens for very fast samples, so very high conduct or for high conductive samples where the measurement time is very low. These both effects need to be corrected, but most of the available models just consider one of these effects. Here, Linsize is quite unique, having this so-called combined model from from Dr. Dusa, who considers both effects at the same time, and this is a more or less universal evaluation tool, being able to evaluate almost every kind of material. Basically summarizing the laser flash features, so the Linsize laser flash is a high performance tool, either with a xenolamp or a laser available, offering different analysis tools. We have different furnaces from cryogenic temperatures up to 2800 degrees Celsius with a high temperature furnace, where you see here an example of that. Here we have then this graphite sample holder for 1 or 3 samples at the same time. So we also have this robot for the very high temperature range. Here you see some different furnace types. This one here on the left is also a customized model for some nuclear application, where we change then the materials within the instrument, being able to withstand this radioactive radiation. Basically, also this laser flash is able to measure insulation materials up to extremely high conductive materials. So summarized maybe 0.1 to 2000 watt per meter Kelvin. And this is here a screenshot of the software, where you see then the simple evaluation where the software does more or less all for you. The next instrument we will have a look on is the Transient Hot Bridge, shortly THB. It's also a transient measurement method, and it is based on the hot wire principle. The THB was developed in cooperation with the German Meteorological Institute PTB, Physikalisch-Technische Bundesanstalt, in Braunschweig, and the first launch was in 2011. And in 2021, we launched a new version of the THB, so that it is looking like that right now. The Transient Hot Bridge is a fast and easy measurement tool for thermal conductivity determination. With special sensors, you can also extract the thermal diffusivity using the density. Also, the specific heat capacity can be calculated. We have grouped the THB into the basic, advanced, and ultimate. Each of the models is capable of measuring a different thermal conductivity range. Basically, the instrument can measure very low conductive materials, also quite high conductive materials. And you can use this tool for solids, liquids, powders, pastes, so more or less the complete range of materials. The temperature range is going from minus 150 degrees Celsius up to 700 degrees Celsius. The basic unit more or less can measure up to 200 degrees Celsius. As the method or this instrument is based on the hot wire, we need some hot wires. So we have here this hot wire is built in a sensor, so that the wires are embedded in a Kapton foil, or we have also this high temperature version where these wires are printed on a ceramic substrate. And basically we have here 4 groups of sensors, the THB sensors for low conductive materials, the QSS sensor for the high conductive materials, the THB sensor with a metal frame for powders, pastes, and liquids, and the hot point sensor for very small samples. Advantages of the THB is that it is a plug-and-play system, so you can disconnect one type of sensor and connect a completely different type of sensor to the same main unit. So you can cover the full range with various sensors using this plug-and-play principle. The measurement principle I will explain a little bit later, but basically what belongs to sample preparation is having 2 pieces of material covering the sensor foil and fitting very precisely on top of each other so that there is no air in between the sample pieces. And to enhance the contact between sensor and sample a little bit better, we typically compress this configuration using here such a sample press or by putting a weight, for example, on top of that. Here you can already see the very basic measuring principle of this sensor. So as mentioned, it's based on the hot wire technique where we have this wires acting as a Joule heat source, but at the same time also record to temperature rise during time. This temperature rise with time will give indication about the thermal conductivity of the surrounding material. So that is why the sensor needs to be embedded within 2 sample pieces so that the sensor is completely covered by the material to test. In case of liquids and also powders, the sample preparation is quite simple. The easiest way is to just get a beaker, fill it up, and stuck the sensor inside. So here is the THB metal frame sensor inserted into a liquid. You just cannot see here the tip of it, just due to the water. And on the right side, you see our powder sample holder, specially designed here for this type of sensor, where you fill up some powder, insert the sensor, and have also the possibility to compress the powder a little bit. All of the previous shown THB or all of the previous sensor types work according to the same principle. So the hot wire, hot strip method, but our sensors are an enhancement of this principle. So the design is different compared to the just hot strip sensor. So we have here some meander shapes and the connection to a Wheatstone bridge for just having a better sensitivity within the measurement. So this is also where the instrument is named of. So this transient hot bridge, transient measurement method, and based on hot wire, but connected to a bridge connection. Here you see again this measurement principle where the sensor serves as a Joule heat source and a resistance thermometer. During the measurement, the sensor emits a constant heating current and also heats itself. The temperature rise over time is then a measure for the thermal properties of the material, where I do have a look onto the bridge voltage, as this is directly proportional to the temperature increase of the sensor. Here you can see a typical signal of a THB sensor, where in purple you see the bridge voltage rising with time. For the evaluation, we have a look onto the slope of the bridge voltage to find out the maximum here, which is an indicator for the thermal which is the point where we extract the thermal conductivity. The decay afterwards is an indicator for the thermal diffusivity of the material. Here you see a screenshot of the software, so it's very simple designed and it's more or less a one-button solution where you just press on start. so that the sensor type is automatically recognized. You can see the temperature reading of that. You define the number of measurements and press on start. But of course, for more experienced user, there's also the possibility within the options to modify manually the measurement time and heating current and so on, so that also here manual measurements are possible. Here you see then the screenshots of the measurement curves on the left side of the THB sensor and on the right side of the QSS sensor, where you directly see the curves look completely different. That is just due to the fact that the alignment of the wires within the QSS sensor is differently, and also the evaluation is different. QSS stands here for quasi-steady state, so that we are exceeding a little bit the transient state, going towards the steady state, but we do not measure so long so that we are in a final steady state. So that's something in between, and we call it then the quasi-steady state sensor. And maybe just having a look here quickly also on the time scale, you see here measurement time is about not even 30 seconds. Here on the lower example, it's about 10 seconds, so that the THB measurement is very quickly to get the thermal conductivity. For the THB, we also offer a lot of accessories to customize the instrument. So a lot of different furnaces, for example, here the Peltier controlled furnace going to sub-ambient temperatures and slightly elevated temperatures. We also have tools for contact pressure control, as well as different sample holders. And for the case, for example, that one cannot cut a large piece of material into two pieces, one doesn't want to destroy it, there is the single-sided sensor based on the QSS principle, where just one sample piece is needed to be able to measure the thermal conductivity, especially useful for high conductive materials. So this was the introduction into the both transient measuring instruments we offer for thermal conductivity determination, and now we will have a look onto the steady state methods. The first of them is the TIM tester. It's the thermal interface materials tester, which is especially designed for so-called thermal interface materials, which act as a gap filler or void filler in between the contact of two different materials, mostly in electronics. So most of you probably know this thermal paste or this gap fillers or thermal pads, where the electronics will be in contact with a heat sink. So to just remove the heat from the electronics to just avoid damages within the electronics. To this kind of thermal interface materials, there are three groups: the type 1, type 2, and type 3. Type 1 are viscous liquids, so something like pastas, greases, or phase change materials or liquids. The type 2 are, let's say, like foam-like materials, so soft materials like pads or the gap fillers. And the type 3 materials are the solids like polymers, metals, or ceramics. For these kind of examples, the TIM tester is designed for. It is also a standardized method according to the ASTM 5470 norm, where this norm precisely describes how the system should be built and how the evaluation should be done. The basic setup of the TIM tester is having here this plates, or we call them meter bars, where the one is heated and the other one is cooled. So the upper one is heated and the lower one will be cooled using an external chiller, and in between the sample will be clamped in. Due to this temperature gradient, a heat flow is established. We'll wait until this heat flow is in a steady state, so it is constant. When reaching this point, we use then this heat flow to calculate the so-called thermal impedance, denoted here with theta, using the sample area, which is the same as the meter bar area, the heat flow, and the temperature gradient over the sample. And this property we use then for the further evaluation, which we see then in a slide later on. The thermal impedance is the sum of the thermal resistances from the top to the bottom, so including here also the contact resistance between the sample and the meter bar. On the slide you can find a more detailed sketch of the TIM tester with its components. The main part here are the meter bars, which contain heaters inside, being able to heat up the sample. In between, we clamp the sample. During the measurement, we also track the sample thickness using an LVDT. A further important part of the TIM tester is this actuator on the very top, so that we are able to control the contact pressure onto the sample. Similar as within the THB method, we want to guarantee a good contact between the sample and the meter bars. You also see the pipes going to the external chiller, being able to cool down the lower meter bar. The main unit is designed for thermal conductivities between 0.1 and 50 watt per meter Kelvin, and as most of the materials the TIM tester is able to determine are used in electronics, the temperature range of room temperature up to 150 degrees Celsius is realized in the basic unit, with some modifications. One can reach also sub-ambient temperatures going down to minus 30 degrees Celsius. Also, we have a high temperature model going up to 300 degrees Celsius. So as already mentioned a couple of times, we offer a high level of customization so that also the size of the meter bars can be customized. Typically, we use round or square meter bars, either 25 or 40 millimeter in diameter or side length. There are also different coatings possible with the meter bars, so that this can be customized as well. Some analysis need the analysis also of a pressure dependency. This can be done using the software so that we can control the pressure with different actuators on top of the instrument. Lower or higher pressures can be realized onto the sample. So with our most powerful actuator of 5 kilonewton, here you see a picture of it, we can realize a pressure of about 8 megapascal onto the sample. Most of the samples we test are quite thin, so that the sample thickness is mostly ranging from 100 micrometers up to 5 millimeters. Basically, thicker samples can be measured as well. Before I mentioned that we measure the thermal impedance of the material, so the sum of the thermal resistances as well as the contact resistance. But in practice, this contact resistance is not of interest or should be not included in the end result. Because of that, the typical testing procedure is the following, so that we measure 3 different sample thicknesses where we obtain the thermal impedance, plotted in a way like that. So having the thermal impedance in dependence on the sample thickness, we find out that it's a linear relation, as for each sample thickness, the same contribution is the contact resistance. This corresponds then here to the offset on the y-axis, and the inverse of the slope of this linear relation corresponds to the thermal conductivity of the material without the contact resistance. So that is a typical measuring procedure. Here you can see an example of a thermal conductivity with about 3.5 watt per meter Kelvin, and we found out here as well the contact resistance. Here you also see the TIM tester software where we have different fields, setting up the sample, measurement, having a look at the current values during the test, and in the end, there will be an automated report listing all the individual points as well as the graphic representation of the impedance versus the sample thickness, and in the end, the total result. The software offers also, which is not shown here in detail, different modes for testing materials. So grouped also into type 1, type 2, and type 3 materials, where each of the measurement mode is specialized to different material class, so either paste-like, foam-like, or solid. So coming now to the last instrument we will have a more detailed look at is the heat flow meter, the steady state measuring method, also based on this plate method. The heat flow meter is especially useful for insulation materials, so materials with a conductivity lower than 1 or even 0.1 watt per meter Kelvin. So mostly this tool is for insulation materials, building materials, and so on. It's also a standardized measuring method. And here the sample, as it is a building material, typically larger samples are required. A typical sample size is, for example, 30 times 30 centimeter with thicknesses 1 to 10 centimeter. The measurement principle is basically similar to the one I have shown already for the TIM tester, where we have the two plates. One of them is heated up and the other one is cooled, so that we will have here the temperature gradient over the sample, establishing a heat flow. We wait until the heat flow is constant, so in the steady state. The heat flow we measure here directly using so-called heat flux transducers, and this signal gives then the information we need to find out the thermal conductivity. We also determine the so-called U factor, which is the heat transfer coefficient, which is often used for building materials, being able to group the different building materials and compare them. Also, the thermal resistance of the material is determined using the heat flow meter. The difference compared to the TIM test is, on the one hand, the size of the sample, the thermal conductivity range, and here within the heat flow meter, as we use the heat flux transducers, we need to calibrate this reading with a reference material. So coming now a little bit to the end, we will have a look onto a summary of the different instruments. So starting with the transient methods, on the one hand, we have here the laser flash analyzer, which is a very universal tool, being able to measure the thermal diffusivity of insulation materials to high conductive materials, mainly for solids, but with some modifications also useful for liquids, powders, pastes. For example, the laser flash covers the widest temperature range. So depending on the furnace type, one can go down to minus 125 degrees Celsius. But on the other side, with a special type of furnace, we can reach up to 2800 degrees Celsius. The samples are quite small, typical in the range of diameter 10 to 1 inch diameter, sample thickness starting from a few hundreds of micrometer to a few millimeter. Mainly the sample thickness range is between 1 to 3 millimeter. The second transient measurement method we offer on our product range is the transient hot bridge, the THB, which is designed for measuring the thermal conductivity of insulation materials to high conductive materials. Also, um, here the solids, liquids, pastes, and powders can be determined. The temperature range is a little bit limited from minus 150 to typically 200 degrees Celsius. With the ceramic version of the sensors, one can go up to 700 degrees Celsius. Mainly, the samples for the THB are much larger compared to the laser flash, also as you need two sample pieces being able to perform a measurement. So mainly the sample size is 40 times 20 millimeter range. The thickness is also mainly in the 3 to 10 millimeter range. Going now to the steady state methods, where we have the heat flow meter, which is designed for insulation materials or building materials with a quite low thermal conductivity. We can determine here the conductivity, the so-called U value, and the thermal resistance in a quite low temperature range, but this is the most used one for such insulation materials. Mainly the heat flow meter is used with solids or compressible materials like foams, for example. We need here very large samples in the centimeter range, 20 to 60 centimeter are needed, and also the thickness is more in the centimeter range. The TIM tester is measuring according to a similar principle. We determine the thermal conductivity of typically thermal interface materials with a moderate thermal conductivity. Temperature range is also quite limited, up to 150 or 300 degrees Celsius, but we can measure here a broad range of materials like solids, compressibles, or pastes, and the sample size is in the range of 25 to 40 millimeter, and thickness is mostly in the lower millimeter range. I have shown to you now 4 of the instruments we offer for thermal conductivity determination, but of course the most important question is, what type of instrument should I choose when I have a special application? The selection of an instrument for thermal conductivity determination is not that simple and sometimes not very straightforward. So one needs a few information to be able to decide which type of instrument is the best suiting one for the application. First of all, of course, the type of material should be known. So if one has a liquid, then the first choice would be the THB, for example, as it is the most easy one to use with liquids. But on the other side, one also has to have a look onto the temperature range, as for example, THB in case of a liquid is just limited to 200. If one tests a high temperature oil or wants to go into a liquid phase of a material starting at higher temperatures, then the THB is not interesting anymore. So one needs to collect the information of the material to be able to determine the right method, the right instrument, and this is what we do here at Linsize. When we get a request for a measurement, we just collect this type of information, so type of material, expected thermal conductivity range, temperature range, if there is a restricted size and thickness of the material, if there are some further measurement conditions, and depending on these answers, we select the type of instrument. For some applications, various instruments should be capable of measuring this kind of material, and then we just, for example, just use the one which is the most convenient one and does not require the highest effort. So yeah, on our website we also have, for example, a indication of which instrument is capable of measuring different materials. So on our website, you find this table where it is indicated on the sample type which instrument fits very good, which might fit, and which doesn't fit at all. Also, if you are looking for a specific property like thermal diffusivity, there are some indications which model offers which property. Additionally, also the temperature range, so that this table here on our website is a first indicator on which model might be suitable to realize your application. On the other side, our specialists from the lab and from the sales will help you in deciding which tool is the best one for measuring your application. As you might have recognized, I was talking mostly about bulk materials, starting from a few hundreds of micrometers, lowest one, thickness one, but typically in the millimeter range of sample thickness. LinSize offers also some tools for thin film analysis, so starting from nanometer going to a few hundreds of micrometers. This analysis is also crucial as the physical properties of thin films might differ completely from the bulk material. So the parasitic surface effects are much stronger due to smaller dimensions and higher aspect ratios. So especially in the semiconductor industry, this investigation of the thin films is very important. This analysis of thin films is more complex compared to the bulk material analysis, but we have in total 3 instruments, 3 techniques being able to measure thin films. For example, the TFA using such chips is capable of measuring nanometer scaled materials. The FDTR or TFLFA, where a sample is here, is useful for measuring semiconductor material with a very smooth surface. And the newest instrument is here, this PLH, standing for periodic laser heating, is especially suitable for polymeric or ceramic or metallic thin films in the lower micrometer range. These 3 techniques and instruments will be described in a separate webinar. This is scheduled for June. Currently, you can already register on our website for that. And so that I did not focus right now on this type of analysis as this is more complex and would just be too long for one webinar, so that we separate it into 2. Now I'm at the end of my presentation. I would like to thank you very much for your attention.